So this is exercise number 2, where we are going to use a cylindrical coordinate system to express the equations of motion components. So what we have here is a system, is a conveyor actually. It's a conveyor that has a swing arm, and this swing arm, when it rotates, it pushes cans through the production line. So I have a picture here that shows a real system conveyor, but I'm going to draw here how is it like real life. So basically you have here an arm, it says fish somewhere here, and like this. This is the arm that swings. So when the arm rotates, say in this direction, and you have some product here, let's say can. So when the arm swings, it will push the can in this direction. Okay, it pushes the can to move this direction. Let's say this is O and this is A. So the arm OA moves with a constant speed of theta dot is equal to 4 radians per second. So it rotates here with a constant speed of theta dot is equal to 4 radians per second. Now they give me an approximate equation for this path, and that equation is R is equal to 0.1 theta. So the mass is 0.5 kilograms. This is the mass of the can, and they ask to calculate the force exerted by the arm OA on the can at the instant theta is equal to pi radians or 180 degrees. They asked me to neglect friction, so it's good. So the question is, given that the spiral function R is equal to 0.1 theta, and it is in meters, and theta in radians, the question is, find the force applied by the arm OA is equal to what when theta is equal to pi radians is equal to what? Okay, so let's solve this problem together. First, we notice that they asked me for the to calculate a force. They asked me to calculate force. Since they asked me to calculate force, it means I need what? I need equations of motion. And in the equation of motion, the equations of motion, you cannot set them up without free body diagram. Okay, so you need to draw free body diagram first, then you set up the equations of motion, then you calculate the unknowns. So this would be our plan. This would be our plan. So what are the forces that are present? First, we have to recognize the fact that this system is horizontal. So what does it mean? It means this is a top view, and we are dealing here with forces on the plane. Okay, we are dealing with the forces on the plane because the weight, for example, of the can is actually downward. The weight of the can is downward, and there is a reaction force that is upward. That's not our concern. Now our concern here is the forces that are on the plane. So what do we have here? We can draw here the can and see what are the forces. So this is the can, and what we notice that first, when the arm, let me just show here, the arm applies a force on it. That force is the force that is pushing the can to follow the spiral shape. So first we have a force in this direction that is perpendicular to the arm. Okay. So if this is the arm OA, the force FOA is this. And this is the force that we are looking for. Now as the arm pushes, okay, when the arm rotates, it pushes the can towards the direction of the force FOA. So what happens? Look here carefully at this side of the conveyor. We have two sides. So this side and this is the other side. What you see here is that as the arm pushes, this side of the conveyor is supporting the can, and it doesn't let the can to move outside. It doesn't let the can to move outside because it is supporting. Since it is supporting, it has to apply what? An action, and that action is what we call the normal reaction force. So it is what? A perpendicular, a force that is perpendicular to this surface at this point. Okay, it is perpendicular to the surface at this point. So if I draw the surface, so it is perpendicular to this surface. Okay. Now this M is important because without it, if you forget to represent the action of this side of the conveyor, as the arm rotates, it pushes the mass, and the mass will just drop out of the track. It just drops out of the track. So since it is important to have that support, this means that we will have a reaction force N of that support. Okay. Now let's draw it now properly, but just remember that you have to isolate the mass. You have to isolate the mass. It's a free body diagram. It means you have to free the body that has a mass. Okay, you have to free it. So we only draw the can. That's all. You don't draw anything else, and anything else that is contributing to the dynamics of the system surrounding, the environment surrounding the mass, you have to remove it and represent it using forces. Okay, using forces. So I'm going here just to draw just the path. I use the gray to say that, in other words, that it doesn't exist. Okay, this doesn't exist. Just to show. Okay, then I'm going also to show here the support. I mean the left side of the conveyor belt, and this is the other side. Notice that I purposely kept a distance. I purposely kept a distance here to show that this is not contributing at all. Okay, at least at this position, theta. Okay. Now let's draw the forces. Now we start with the force applied by the I'm going to draw it here, applied by the arm OA. So now that I have represented the mass as a free body, I can now put the all the forces. So we have a normal reaction force in this direction. This is N, and the force exerted by the arm OA, and it is perpendicular to that arm, so it will be force exerted by the arm OA is perpendicular to the arm. So this will be the force FOA. That is the force I'm looking for. Good. Now notice here that I have a very particular situation where I almost have these two forces N and FOA that are perpendicular to each other. I have to reiterate that this is not the always the case. This is not always the case. It just happens that we have it like this. So as I said, this is a very particular case. So this is very particular case where you have an almost 90 degrees angle between N and FOA. This is not always the case. So I draw here a case that is general. So here a general case. Okay. This is a general case where we have N and FOA. The angle between them is not necessarily 90 degrees. Okay. So we keep it now this way. So I'm going to put this aside. Okay. So this is the free body diagram. Now that I have the forces, I can go ahead and write the equations of motion, set up the equations of motion. But I'm looking only for FOA. Since I'm looking only for FOA, I have to be very careful and use only the set up only the equation of motion in the direction of interest only. So based on the graph given to me, I draw here the origin, and I extended the position vector to get the radial axis, and perpendicular to this axis will be the transverse axis theta. Okay. So what I'm looking for is the force FOA, which is in the transverse axis direction. So what I do, I have to set up the equation of motion first only in that direction. So we say sum of the forces in the transverse direction is equal to the mass times the acceleration in the transverse direction. So what are the forces in the transverse direction? First, I have the force FOA, and it is positive because it's in the same direction of the transverse axis, theta. Then what we have the component of the normal reaction force on the transverse axis. So we are talking about this component. This component will be what? It will be n times the cosine of this angle. So let me just show the angle here of this angle. Cosine times cosine the angle. What is that angle? Well, this angle, actually, if you remember the if you have watched our lecture before, you see the link in the description. This is psi. This is the angle psi, because the angle psi, it is either between the radial axis and the tangential axis, okay, or between the normal axis and the transverse axis. It's the same thing, okay, either between the radial axis and the tangential axis, any force that is in the tangential axis, or between the transverse axis and the normal axis. So R and theta here we are talking about the polar coordinate system, and T and N we are talking about normal and tangential coordinate system. So just remember this, okay? So we have N cosine sine, N cosine sine, okay? and cosine psi. Let me just put this aside here. So plus, it is positive because in the same direction, that component n cosine psi, it's in the direction of the transverse axis, so n plus FOA plus n cosine psi. That's these are the only forces that I have. Is equal to the mass times the transverse acceleration. You have to be careful, this is transverse acceleration and it is not the angular acceleration. Now I have to put here what I'm looking for. So this is what I'm looking for. Do I have the normal reaction force? I don't have it. Do I have psi? I don't have it also. Do I have a theta? Also I don't have it. So I have to look for n. I have to look for psi. I have to look for a theta. Once I have these three, I can calculate FOA. Now let's start with the n, which is the normal reaction force of the left support of the conveyor. So since it is a force, I will use an equation of motion, and in this case we will set up the equation of motion in the direction of the radial axis, So this is one. There we go. Here we have sum of the forces in the radial axis is equal to the mass times the acceleration in the radial direction, or we call it shortly a radial acceleration. Clear? Yeah. Now, the component of the normal reaction force on the radial axis is this. So, we have here n sine psi. Okay, n sine psi, because it's opposite to the angle psi. So, and it is negative because it is opposite direction to the radial axis. So we have minus n sine psi, and that's the only force that we have, because FOA, it is entirely in the direction of the transverse axis. So is equal to the mass times acceleration in the radial direction, or radial acceleration. Now, imagine the case that you have the radial acceleration. If you have the radial acceleration, you have psi, you can calculate n, but you still have problem with a theta. Okay, you still have problem with transverse acceleration. So let's put here n. Now we are looking for n, but I still don't have psi, and I don't have the radial acceleration. Okay. Now, before going to the radial and transverse accelerations, we have to calculate first psi. Okay, so psi is equal to what? If you recall, we said psi is equal to tan inverse of r over dr over d theta. Okay, r is given to me is equal to 0.1 theta. Then I can calculate the derivative of r with respect to theta. It gives me 0.1. Now, theta is equal to pi radians. What we have? We have r is equal to 0.1 pi meters, and dr over d theta remains constant at 0.1. Okay, so this means that psi is equal to tan inverse of what? R, which is 0.1 times pi divided by 0.1. Okay, so this and this are cancelled, so we get tan inverse of pi, and this gives me about 72.3 degrees. Okay, great. Now we can go back here and ensure that we have green tick means I have it now. So what I am left with is the radial and the transverse accelerations. Okay, the radial and transverse accelerations. Okay, now from the previous lecture we have the radial acceleration is nothing but the second derivative of the position r minus r, the position times the angular speed squared, and the transverse acceleration is equal to the position times the angular acceleration plus 2 times r dot theta dot. We have theta dot is constant and it is equal to 4. So this is 4 radians per second. And theta double dot is 0. Why? Because theta dot is constant. So if the angular velocity is constant, the angular acceleration is 0. So what we are left with is finding this guy, r double dot and r dot. Okay, so we have r is equal to 0.1 theta. So this means that r dot is equal to 0.1 theta dot. Here remember the derivative is with respect to time, so here we mean dr over dt. Okay, so dr over dt is basically dr over d theta times d theta over dt. Okay, so look here carefully. We did nothing when we multiply it by d theta and divided by d theta. So look at this. This is simply theta dot. Okay, this is simply theta dot, and dr over d theta we have it is equal to 0.1. Clear? Now we have 0.1 times theta dot. Theta dot is actually 4, so it gives me 0.4. Okay, the unit of course it has to be meter per second. So likewise r double dot is equal to 0.1 theta dot, theta double dot, and this gives me 0. Okay, now we can go back to AR and A theta calculator. So AR is equal to R double dot minus R theta dot square. R double dot is 0. So we will have minus R, which is 0.1 pi times theta dot square, which is 4 square. It gives me approximately 5 meter per second square. And A theta is r theta double dot, which is 0, plus 2 times r dot theta dot, and this gives me 0 plus 2 times r dot, which is 0.4, times theta dot, which is 4, and this gives me 3.2 meter per second squared. So now that I have AR and A theta, okay, so we have now AR and A theta, I can calculate not only FOA, I can calculate also the normal force due to the conveyor support, the left one. So if you do the math, you should be able to calculate both N and FOA. So N will be equal to about 2.62 newtons, and FOA is 0.803 newtons. And this concludes the solution to the can on a conveyor belt with the swinging arm.